All right, we're going to do problem 54 from chapter 8. We have, this problem describes a child who has a specific weight sliding down a playground slide with an angle of 20 degrees. It describes a coefficient of kinetic friction between the slide and the child, and it asks how much energy is transferred to thermal energy. And it said if she starts at the top with a certain speed, what is her speed at the bottom? So here's, I'm going to draw a sketch real quick of our slide. Probably isn't to scale very much. I'm not a really good drawer, but here's the person, and the child is going to slide down the slide down a 6.1 meter playground slide. I'm not exactly sure what that means in terms of if that's this distance or the height. I'm going to guess it's the height. No, that seems high. It seems really high. But it doesn't really matter. We can figure it out. It tells us that it's 20 degrees with the horizontal. And so in terms of actually working the problem and talking through it, it doesn't really matter what the exact height is. But it tells us the weight of the child, right, which a lot of times we like to write as like gravitational force, is equal to 267 newtons. Slides down this slide with an angle. It has a coefficient of kinetic friction that is equal to 0.10, and it asks how much energy is transferred to thermal energy. During this time. So it's not really clear to me exactly what information that we want out of here. Because I don't know if this is 6.1, so I could be making this a little bit more difficult, that it doesn't really matter. What we want to know is how much is converted to thermal energy. And so the way we get that, right, we talked about that in class, that the change in the thermal energy is going to be equal to the work done by non-conservative forces. So the non-conservative force here is the frictional force, right? So what we're really asking us to calculate is the work done by the non-conservative force here, which it turns out that the frictional force is constant. So it's a constant force that doesn't change throughout time. So because it doesn't change, we can calculate the work as the scalar product of the force, the frictional force in this case, with the displacement, delta L. That simplifies. If it wasn't constant, we would need to use the integral form of that expression. And that equals the, right, so what that means is that we have that quantity. Our frictional force, in general, the expression, we calculate kinetic frictional force by mu k times the normal force, the force normal. And so we can do this a number of ways. We can write this down. Oh, I'm sorry, that shouldn't be arrowed, right? That's the magnitude of that. So we can write mu k times the normal force acting on this girl, and the scalar product of that. So that's going down the ramp, right? And we can write the scalar product of that with this displacement delta L. So down the ramp, let's actually write a coordinate system like this real quick, where positive x is down the ramp and positive y is perpendicular to the ramp. So that means that this frictional force acts in the minus I hat direction. And the scalar product of that with the displacement, which the displacement here is some distance along delta x in the I hat direction, which that delta x, if we called this vertical portion 6.1 meters, then this the delta x would simply be, delta x would be, what would that be? Sine theta, right? The distance here would be sine theta times 6.1 meters, right? Would tell us the length that this person has traveled, where theta, I think in the problem, was 20 degrees. That tells us the delta x that we're interested in. We'll just leave it as delta x for right now, realizing the child slides down this distance, delta x. But the forces are in the opposite direction, so this gives us a negative value of mu k times the normal force times this displacement delta x. The normal force for a situation on a ramp, I'm not going to go through it in gory detail, but we use Newton's second law to determine that. You should go back and review that if you forgot how to do that at all. I'm going to draw a little sketch on my person real quick, just to help remind me. I always like to draw a sketch. So there's our weight is going down, our normal force is this direction, which means that for our sketch we need We need to use that's theta, so we need to use cosine of theta to tell us what the normal force is. So cosine of theta times mass times gravity times this delta x will tell us the work done by the non-conservative force in this case. Right? So something I think that we actually talked about in class, and I wasn't completely satisfied with how we kind of put everything together. And the more I look at it, I think that I need to make a special note here that whether or not I said this incorrectly in class is kind of up for grabs, I suppose. But this isn't actually the change in thermal energy, right? This is minus the change in thermal energy, because just like when we called the work done by conservative forces led to minus the change in potential energy of the system, I think we also need to make sure that we include a minus sign when we talk about the work done by non-conservative forces, that it's minus the change in thermal energy. And so I don't think I did that above here, because I think that's really important, because we also, when we get to the expression and talking about the change in mechanical energy, that needs to be equal to the difference in thermal energy, right? If we sum all those quantities up, they should be equal to 0. So for a case where the kinetic energy is decreasing, the thermal energy needs to be increasing. And I think the way we currently have it written out, I don't think it actually works out that way. I'll talk about that a little more on Friday, or maybe send out an email. But just in case you see this video before then, make sure you watch out for that. So that being what this is, the actual change in thermal energy then is going to be a positive mu k times mg times delta x times cosine of theta. And then delta x, where delta x is this sine theta 6.1 meters, which may or may not be correct. Could just be 6.1 meters. Plugging all that information in tells us the change in the thermal energy. So that's fantastic. It's a positive change, right? It's heating up. And if we had left it just as before, it would be decreasing, like that doesn't make any sense. Like that we would be gaining energy. Like the person goes down, and by virtue of the fact that it has friction, the person gains energy. That doesn't make any sense, right? The part B of this particular question says that if she starts at the top with a particular speed, what is her speed at the bottom? And so this asks us to calculate the total change in energy, right? We know the total change in energy is going to be 0. That's of all the energies, right? That's the change in kinetic energy plus the change in potential energy plus the change in thermal energy. And all of those are going to sum to 0. Which is kind of further evidence. I think in class we may have written it with this term on the right side as being positive, and that just doesn't sum up. We gain energies. We'd create or destroy energy if we did that. So this is a situation where we want to look at the final kinetic energy, the initial kinetic energy. We want to look at the final potential energy and the initial potential energy. And we already calculated the change in thermal energy, so I'm just going to leave that term as it is. We'll just plug in the number that we had for that. The final potential energy at the bottom is going to be, we could set that equal to 0 just because it's convenient. We know how high up in the air she happens to be, so we can use minus mg delta y. So that tells us the initial value of her potential energy. We add to that our change in thermal energy. The initial kinetic energy, so in the first part of the problem, if she were to start from rest, the initial kinetic energy would be 0, but the problem tells us that she has an initial kinetic energy that depends on her initial velocity and wants to know what her final velocity is going to be. So we simply do this calculation where we move all of these terms. We know everything in this term, and this term. We're going to move all of those over to the right side, making sure that we account for all of our signs carefully, and then we're going to multiply by 2 and divide by m and take the square root of all of that stuff. Let's see if I can write that all down in one fell swoop. So it's a whole mess of stuff. We're going to get 1/2 mvi squared plus mg delta y minus the change in thermal energy, all of that times 2 and divided by m. Yikes, right? It looks scary, but these are just simply constants, right? I prefer to not put in numbers. I would encourage you also to not put in numbers right away. It's something we want to be able to see where all of this stuff comes from and know that, oh, here we have some energy, we have some energy, we have some energy. Everything here is going to be great. It's exactly the kind of units that we need.